We've introduced AR processes, autoregressive, and MA processes, moving average processes. What if we had a noise process that had both features from autoregression and moving average? We can combine an AR operator of order P and an MA operator of order Q by simply saying this. The autoregression operator operating on the data values is equal to the moving average operator operating on a white noise series. It's more usually written like this, where I just expanded the operators and put in lagged values and then moved everything to the right-hand side except the data itself. If the ARP operator is invertible, we can operate on both sides with the inverse and say this, that the data value is the inverse autoregression operator operating on the moving average operator operating on the white noise process. And that defines this operator, uppercase Greek letter psi. It is generally an infinite number of lag operators, and it would have an infinite number of coefficients, psi1, psi2, etc., and could be put in this form. Notice that the n equals 0 term requires that the psi sub 0 coefficient has to be 1, but beyond that, all the psi coefficients can be non-zero and therefore lead to non-zero factors of powers of the lag operator. In this case, if we take an example of an ARMA 1-1 process. Now, the autoregression operator is 1 minus phi times the lag operator. The moving average operator is 1 plus theta times the lag operator. For the absolute value of phi less than 1, the autoregressive operator is invertible. In fact, it takes this form that we've seen before, and we would have that psi is equal to the inverse times the moving average operator, which we can expand algebraically to be like this. And you can probably see what the form is. We can put it in an equation series form like this. By the way, this sum should be from n equals 1 to infinity. That's a slight typographical error. In that case, we would have, these are the coefficients, and we can pull them directly off of the expansion we got previously. Of course, the psi sub 0 term is 1, as it always is, and these are the terms psi for n greater than or equal to 1. If we know the psi coefficients, we can compute the autocovariance function, and therefore the autocorrelation function, by using our possibly now familiar formulae. If we work out all the algebra, and you might want to do this because it's kind of fun, I think, and is certainly a learning experience, you can figure out that the autocorrelation function at lag h is equal to this whole big messy expression, which we can simplify as being some constant times phi to the power of h, where here is the constant which depends on both phi and theta, but they're both constants, so lambda is a constant also. Now that's a rather interesting, and this expression is kind of messy, but this one's actually rather simple, which shows that the autocorrelation function of ARMA 1-1 noise actually has a reasonably simple form. Now there are many uses of ARMA models, and we'll have a lot more to say about that in future lessons. In particular, we can often use them to predict what noise values will be. Not very far into the future, but we can make useful predictions. But there's one use I'm going to mention right now. You may remember, in fact you probably do, when we estimated autocorrelation corrections for regression, we used something called a variance inflation factor, which is 1 plus twice the sum for all lags greater than 0 of the autocorrelation at that lag. Now there is a problem with practical application of this. When we have a finite sample of actual observed data, we might want to estimate what are all the autocorrelations. But we can't go to infinity because we don't have an infinite number of data values. And the Yule-Walker sample autocorrelation function, it's only an estimate. It's not an exact value, and it's a biased estimate. We probably can estimate one or a few autocorrelation values reasonably accurately, but we couldn't possibly hope to estimate all of them directly from the data. However, if we have a good model of the noise, then we can estimate just a few of the model parameters and get all of the autocorrelations from that. For example, an AR1 process. In that case, there's just one parameter required, and that is the parameter phi, which happens to equal the first lag1 autocorrelation, since the others are all given by that to the power h. Then we can directly compute our autocorrelation inflation factor as 1 plus twice the sum of powers of phi, which is 1 plus phi divided by 1 minus phi, and therefore we can estimate directly and reasonably accurately our inflation factor by estimating just one parameter, the autoregression parameter, which is easy to estimate because it's the lag1 autocorrelation. As another example, consider an ARMA 1-1 process. Among other choices, we can use the two parameters lambda and phi, where the autocorrelations at lag h have this form. Then, once again, we can compute our inflation factor by the simple formula, and we can even work this out algebraically to make it this very simple form, so we don't have to do an infinite sum. Well, this is one of many applications of an ARMA process approach, but there are a whole lot more that we'll be covering in future lessons. We're going to spend a number of lessons on ARMA models and even more kinds of noise models, because there's more to come, but we leave that for the upcoming days.